UCI CanSat. I'm Emiko, I'm the hardware lead.
Hi, I'm Amy, I'm the operations lead.
I'm Owen, I'm on the hardware team.
My name is Partha, I'm also on the hardware team.
So today we'll be talking about our project's background, previous work and motivation, our goals, objectives, our organization, work, timeline, project requirements, and then finally our current progress and our project's budget. So to start with some background on our project, CanSat is an international design, build, fly competition. It happens every year, and student teams compete to build a CanSat, which has to complete the specified mission. So this year's mission, the CanSat gets launched up to 700 meters, and it has to descend safely. There are two parts to the CanSat. There's a container, and there's a science payload that goes inside the container. And during its descent, the science payload has to come out of the container, and they have to descend separately. And the science payload has to use an auto-gyro propeller to slow its descent. So the previous year was slightly different. We had to descend using an air braking shield that opened up and then was released from the CanSat. We also had a payload last year of 1A, which we don't have this year. What did get carried over is data. We have to record data from sensors on the CanSat and transmit it to a ground station where we plot it in real time. Last year, we placed 17th in the final ranking. So this year, we want to apply our lessons from last year to do a better job, build a better CanSat more efficiently, and hopefully place better in the competition. We also need to lay the groundwork for CanSat to continue in future years. So these are our goals. Our first goal is to place in the top 10 during the preliminary design review. This is a presentation that we give to the judges, and the quality of it determines which teams get into the competition. So we think this is an achievable goal because last year we actually had the top score for the PDR. So assuming we do well there, our next goal is to stay in that top 10 during the critical design review, which also ends with another presentation to the competition judges. And then finally, to finish designing, building, and testing our CanSat hardware for the final competition, which is at the end of spring quarter in June. Our additional goals are to provide all of our team members with experience in the engineering design process. We follow the whole process every year as a competition project, and to represent UC Irvine at the International CanSat competition. So to do that, we have some objectives. Our specific objectives this year are to receive data from the CanSat on the ground station, plot it in real time and log it. We're just going over the top level here. Transmit accurate data from the CanSat to the ground station. Descend using the specified mechanisms, the parachute and auto-gyro propeller, and to be compliant with all of the CanSat competition safety requirements and their launch system. We won't go into these, there's not enough time. So now on to Amy for the team organization.
Hi, so last year we had sub-teams that were controls, telemetry, and mechanical, but this year it made sense to do hardware and software. Hardware consists of the mechanical, where the team members work on the mechanical structure and descent control systems and make sure that everything meets the requirements. There's also the electrical hardware, which consists of the battery and power components, as well as designing the printed circuit board. And for software, there's ground station, which collects telemetry data and makes sure that it plots it in real time, as well as software, which works with the Arduino processor and selects sensors for the competition. And here are our team resources. Professor Rangel is our faculty advisor, and we have 7 students enrolled in units for a total of 600 hours for this quarter. And we also have 3 volunteers who put in 2 units of work. And Emmy is the hardware lead, I'm the operations lead, Sabab is the software lead, and our hardware team is Owen, Jonathan, Joseph, Evan, and Partha, and software is Ryan and Alex. And here's our work breakdown, which is the PDR, CDR, and CanSat hardware for the competition. The PDR is due February 1st, and we're really focusing on designing and making sure that everything is finalized for manufacturing in the CDR phase. The CDR is due March 29th, and we're really focusing on the manufacturing side. And for CanSat hardware, we're focusing on testing all of the prototypes that we made. And here's our timeline, which has our general meetings, any 189 documents, peer reviews, and design reviews. And this is for winter quarter and spring quarter. Notice that winter quarter is when the PBR is due, and spring quarter is when the CBR is due, which is our major deadlines to meet in the competition. And the rest are more documents and peer reviews. And here's Owen talking about the requirements.
Thank you, Amy. The CanSat competition has 55 requirements. Some of the most important are listed here. I'm going to go through the first three, which are the most important of these. The CanSat must weigh 500 grams plus or minus 10 grams and fit in a cylindrical payload section 125 millimeters in diameter and 310 millimeters tall. The total cost of the CanSat must not exceed $1,000, and the descent rate of the container and science payload shall be 20 meters per second plus or minus 5 meters per second, and the descent rate of the payload after being released from the container shall be 10 to 15 meters per second. Here I'm going to outline the progress we've made so far. We're going to start with the container structure, then move on to separating the container and payload, then deploying the auto gyro propeller, and connection between parachute and container, then the science payload carbon fiber structure, the material selection for the payload and container, the power budget and electrical system, and then the ground station software development. So starting with the container structure, we chose an easy to manufacture cylindrical design made up of low density polyethylene and 3D printed ABS. We agreed on a 1 centimeter clearance between this container and the rocket payload section. And we prepared a CAD model of this container with the end caps and the sidewall, and identified the materials and manufacturing plan. The next step for this container will be to order these materials, 3D print the end caps, and assemble and test the prototype. The next part of the progress is the container separation mechanism. This mechanism will need to separate at a specific time so that we can release the payload at the correct height, and it will be a nichrome wire latch mechanism made up of 2 3D printed parts, a nichrome wire which will heat up and melt a length of fishing line and release the latch, and a screw into a threaded insert that is used to tension this line. So the next step for this latch, we already have the design made. We're going to 3D print the 2 sides of it and order the nichrome wire and the fishing line, and then assemble it for testing. So next I'll pass it to Partha for the auto gyro.
Thank you, Owen. So one of the major parts of the competition is the auto gyro descension mechanism. Basically, this is just a set of propellers that will passively slow down the descent of the satellite. And so we had to design a mechanism that will unfold these propellers once the satellite has been released from the container. So we went with a lightweight design that's simplistic with almost no moving parts. So we decided just to use an elastic band that will have the propellers in the natural position as shown right here. Oh, I apologize for that. I apologize for that. This is the natural position in the bottom right corner. However, when it's folded up, it will be in the position in the top right corner. So far our progress is we've made a conceptual model as shown, and we have also selected majority of the components that we are planning to use in this mechanism. And now our next steps is to actually select and calculate the propeller size we want for this descent rate of 10 to 15 meters per second. We're going to update the CAD model with all these different components that we have selected, and then finally purchase the components and test and assemble the prototype and make sure the propellers won't catch on the container. Our next step in our progress has been related to the science payload carbon fiber structure. We selected 16-inch carbon fiber because of its lightweight nature as well as its high strength. And we have made a variety of designs as shown on the slides here. And so our main concerns in this payload structure is the strength of the structure, the weight, as well as the ease of mounting components. Our finalized design is this hexagonal structure, and we chose this design because of the greater surface area for mounting the electronics, and the circles in the middle also allow for ease of wiring and wire management. And our next steps is to actually make some minor changes in our team meeting to make sure the electrical team is alright with this design. we need to purchase the 16th inch carbon fiber and epoxy, and also lay out and make the drawings for all the pieces to be sent to the machine shop and manufactured. And finally, we want to assemble the prototype structure. So in our selection for the science payload design, we had to run some simulations. This is our last year's design, so we decided to run a 500 Newton load on the bottom surface where the CanSat would impact the ground, and the 500 Newton load was calculated based on the 10 to 15 meters per second descent rate of the satellite. And so we found that there was a maximum stress of 1.438 gigapascals, a maximum displacement of 3.25 millimeters, and a factor of safety of 2.1. Comparing this to our current design, we found that the stress has decreased to 564.3 megapascals, and the displacement is still the same at 3.25 millimeters. However, safety factor is now 6.2. I'll now pass it off to Emiko to talk about the electrical systems of the satellite.
Thank you, Partha. So the electrical system progress has been, we selected all of our sensors to meet competition requirements. We selected our microprocessor, we made our power budget so we could choose our battery. And next we're going to take this block diagram, turn it into a real circuit diagram, and continue working on our custom PCB, which will connect all of our off-the-shelf sensor modules with less wiring and therefore fewer wiring errors and less wiring weight. We've also made some software progress. Our software team was able to calibrate our gyro sensor to output roll, pitch, and yaw, and they were able to receive data over serial from their Arduino, so now they can start plotting that data in their ground station development. On the next slide, we just have some data that was pulled from the gyro sensor during their testing. And now on to Amy for the budget.
Thank you. So here's our budget. We cannot exceed $1,000, and currently it costs $520 to complete one CanSat. And that mostly goes into the structure and sensors, but also the descent control, electrical, and data transmission. Currently, our project budget is around $1,540 because of the travel cost, as well as trying to make multiple prototypes of the CanSat. And we're hoping that the 189 fees and Europe funding will help with this, but we're also looking for sponsorship to get the travel expense. And thank you for listening to our presentation.
Thanks.